The scale of the universe is truly immense. In this vast abyss, an incredible variety of objects can be found, from barely visible rocky debris to gigantic galaxy clusters. And today, we're going on an amazing journey to the furthest reaches of the visible universe. Our journey begins at the very center of the majestic Milky Way. We will stop near its dazzling core, visit impenetrable dust nebulae and sparkling star clusters, and then touch the mysterious halo. After that, we will embark on a fascinating journey through cold and dangerous intergalactic space permeated by destructive radiation. This journey will take us to some of the most unusual galaxies found in the vast emptiness of deep space. Covering billions of light years of space, we will plunge into the mysterious depths of giant voids, and then get to the furthest reaches of the meta-galaxy. This will allow us not only to see the distant past of our universe, but also to take a peek beyond its borders. Let's get ready, and we begin.
Kosmo.
The vast outer space. Long before telescopes had been invented, people could observe a light strip crossing the heavens. The fascinating and mysterious phenomenon prompted a multitude of legends, but it took thousands of years of scientific progress to finally account for it. It turned out that the Milky Way wasn't a path of gods. What it is the dissipated light of billions of stars too remote to distinguish each one separately. The idea of the stars around us making up part of a single structure of enormous dimensions was first suggested by Immanuel Kant back in 1755. He also assumed that some nebulae discovered by scientists could in fact be remote star clusters, that is, other galaxies. This ingenious guess was well ahead of its time, with the philosopher's contemporaries initially dismissing it. Only in the early 20th century did the progress of observation equipment enable scientists to confirm the existence of other galaxies, and in 1936, Edwin Hubble devised a classification system. Many of its principles are still referred to by scientists today. According to this system, the Milky Way falls into the category of barred spiral galaxies, although it took a long while before it had assumed its today's looks. Our galaxy is quite an old one, since the stars in its central globular clusters were born as far back as around 13 billion years ago. At the same time, there are some areas in the Milky Way where stars are actively born, which means that there is always a fresh supply of young stars. The collected data points to the fact that the Milky Way is a comparatively large galaxy in astronomical terms. The diameter of its disk measures as much as 200,000 light-years, with a halo reaching out into space much deeper yet. Our galaxy is home to at least 200 billion various stars, as well as 25 to 100 billion brown dwarfs. In addition, it contains over 1 trillion planets, countless small celestial objects, as well as clouds of cosmic dust and interstellar gas, which may reach gigantic dimensions. At the same time, regular matter accounts for a small ratio in the galaxy. Around 90% of the Milky Way's overall mass is the so-called dark matter. The amount of light emitted by this mysterious and widespread substance is negligible. However, dark matter plays an active role in gravitational interaction. Even though most of the galactic mass remains invisible, we can still calculate it. To that end, scientists refer to stars' trajectories of movement around the center of the Milky Way. According to the estimates, the overall mass of our galaxy reaches 0.8 to 1.5 trillion solar masses. The structure of the Milky Way is quite elaborate. We'll start our journey today from its center. This area of the galaxy is shrouded in massive clouds of gas and dust, but by happy chance we can observe it through the so-called Bardes window, an area of space with lower amounts of dust. Just like most spiral galaxies, the Milky Way has a supermassive black hole in its center, which is surrounded with an accretion disk with a radius roughly 3 light-years. Dubbed Sagittarius A star, it is the closest object of this class to us. Its mass is 4.3 million solar masses, and its radius isn't over 16 million kilometers, which is 3 times smaller than Mercury's orbit. The first data about the nature of the object in the center of our galaxy was acquired in the course of long observations and thorough calculations. Only as recently as on May 12, 2022 was it possible to get the first image with the help of the EHT network of radio telescopes, and so the earlier hypotheses were confirmed. The area in the center of our galaxy is highly populated. More than 6,000 stars have already been detected within 3 light-years from the black hole, with the orbits of some of them defined rather accurately. For example, there is a white-blue star, designation S62, which is 17.8 astronomical units away from the black hole on its closest approach to it, while moving at 6.7% the speed of light. Classical mechanics laws are inadequate for description of the trajectory of movement of a star as swift as that because of relativistic effects. Just to illustrate, the axis of its orbit shifts by 75 angular minutes with every completed orbit. Besides, when crossing this area in space, we can see several large star clusters with a total mass of around 1 million solar masses. And slightly further, roughly 200 light-years away, another massive black hole is likely to be lurking, whose mass should be around 100,000 times that of the Sun. Traveling further on, we will reach the central molecular cloud, an irregularly shaped area measuring 1600 to 1900 light-years, whose mass is over 60 million solar masses. There are a great many stellar nurseries and gas nebulae, as well as protostars and remnants of supernovae. Most of the cloud's matter is dense hydrogen, whose temperature fluctuates between 50 and 600 Kelvin, which corresponds to 223 degrees Celsius below zero to 327 degrees Celsius above zero. Spectral analysis shows the gigantic nebula to contain carbon monoxide, methyl alcohol, and hydrocyanic acid in addition to hydrogen. Having receded from the Milky Way's center a bit, we will see that it is encompassed by a bulge, a bright and massive formation of an elliptical shape. With its length reaching 10,000 light-years, its transverse diameter is roughly 7 light-years. The total mass of the bulge is as much as 10 billion times that of the Sun. The exact number of the stars cannot be calculated because their radiation blends and renders any estimates unrealistic. Being elongated, the bulge forms the so-called bar stretching for approximately 13,000 light-years and serving as the base for spiral galactic arms. It is here, at one of its ends, that we can see the star cluster Stephenson 2, containing the largest known star today. Its designation is Stephenson 2-18, and its radius is 2,150 times that of the Sun. Unfortunately, chances of finding exoplanets orbiting this outstanding object are quite minuscule. Even if planets did exist at some point in the past, the hypergiant would have swallowed them up while it was expanding. The galaxy's center is home to billions of stars and apparently a great number of exoplanets. Chances of encountering a potentially habitable world among this great multitude are much lower than in less populated areas of the galaxy. This is due to the fact that when a big number of stars are located close together, they destabilize exoplanets' orbits, while their powerful radiation is lethal to all living things. That is why a special area in the galaxy is defined as the habitable zone. It looks like a ring, with a radius measuring 22 to 29,000 light-years, and contains star systems with the most favorable conditions for the genesis of biological life. Worlds encompassed by the ring languish in exposure to excessive radiation, while beyond the ring there's a lack of heavy elements. However, Mathematical modeling shows that stars within galaxies are able to migrate thousands of light years away, thus either leaving the habitable zone or entering it. Consequently, with an exoplanet lying within the zone, it does not automatically suggest favorable conditions on it. Moving on away from the center of the Milky Way, we will have a chance to check out its most impressive part, the galactic disk. It is made up of two components with different properties. The first one, known as the thin disk, measures 1000 to 1300 light-years in thickness, and its visible radius measures as much as 50,000 light-years. On the edge, it gradually dissipates, with the outermost stars lying up to 100,000 light-years away from the galaxy's center. This part of the Milky Way contains around 80% of the galaxy's visible mass, and in fact, it was the last component to have formed. As for the thick disk, its diameter is comparable to that of the thin disk, but it's 4 times as thick and is much more rarefied. It is made up of old stars and is practically devoid of interstellar gas. Observations of some stars in the Milky Way, as well as mathematical modeling, show our galaxy to have swallowed up another one in the period from 11 to 8 billion years ago. This hypothetical cosmic structure was dubbed Gaia Enceladus. It is thought that it contributed several billion stars to the Milky Way, as well as great amounts of interstellar gas and dark matter. It is thanks to this tremendous event that most of our galaxy's thick disk formed, and an additional supply of gas led to a stellar baby boom. There is no doubt that spiral arms are the most noticeable structural elements of our galaxy's disk. Usually 2 major ones are singled out, the Scutum Centaurus arm and the Perseus arm, and 2 minor ones, the Norma arm and the Carina Sagittarius arm. Sometimes a 5th large arm is taken into account, named after the Cygnus constellation. Galactic arms are areas of especially high star count. Most of interstellar gas is also concentrated here, which is why the rate of star formation in the arms is 3 to 5 times higher than in the galaxy on average. They spend the first millions of their lives in open clusters, but gravity forces are too weak to hold the stars close together for a long time. This destabilizes the clusters, and young stars gradually drift away from each other. Traveling along the Carina Sagittarius arm, we will reach a fork that links it to the Perseus arm. The length of this stellar structure reaches 11,000 light-years, and its width measures roughly 3,500 light-years. It is referred to as the Orion arm, and it is here, 27,000 light-years away from the galaxy's center, that the solar system is located. From our planet's perspective, the galaxy's center is seen as a dark abyss. This is the Great Rift, an area of space that shuts out the greater part of the Milky Way from our gaze. It is filled with massive clouds of interstellar gas and dust, and its total mass is as much as 1,000,000 times that of the Sun. Even though the Great Rift is practically not transparent in the optical range, its matter actively emits radio waves and thermal energy. Spectral analysis data reveals that the clouds are mostly made up of hydrogen, with a small percentage of more complex compounds, ammonia, alcohols, and amino acids. The Great Rift is thought to be a potential stellar nursery, but it is going to take a while until the first stars light up in that area. While it is still not quite active, let's move on, beyond the galaxy disk. Even though its bright and clearly defined arms attract a lot of attention, there is more to the Milky Way than that. If we look closer, we will see the vastest and the most rarefied of its components, the halo. Its visible part, spherical in shape, stretches for up to 260,000 light-years away from the galaxy's center, but accounts for just a few % of the total mass. The halo contains a great number of globular clusters made up of remarkably old stars over 12 billion years of age and several tremendous stellar streams. The Sagittarius stream, for example, made up of several thousand stars, encompasses our galaxy in an elongated ellipsis, which is almost perpendicular to the main plane. Modeling shows that all these stars are highly likely to have been gravitationally captured by the Milky Way from a dwarf satellite galaxy, designation Sagittarius DEG. It lies 500,000 light-years away from the Milky Way's center and is going to be swallowed up by it completely within several billion years. Another dwarf galaxy has already met a similar fate. Lying in the Canis Major constellation, it was almost destroyed by the Milky Way, which pulled out millions of its stars by gravity forces. Stretching for 200,000 light-years and mixing with other stars, this string of stars with a total mass of roughly 100 million solar masses has already wrapped around our galaxy 3 times. Apart from bright but rare stars and clusters, the halo contains great amounts of gas, whose temperature reaches millions of Kelvin. Also, great amounts of dark matter are thought to be scattered in the vicinity of the Milky Way, forming the so-called dark halo. Stretching for up to 2 million light-years, it hardly emits any electromagnetic radiation and can be detected only by gravitational interaction. The dark halo remains an unsolved mystery, yet it greatly contributes to the global stability of our galaxy. Predictably enough, the term intergalactic space is generally used to refer to parts of space between galaxies. It is believed that certain portions of these areas are practically devoid of any matter, which makes their composition quite close to that of absolute vacuum. With some of its areas stretching as far as millions of light-years in all directions, intergalactic space is for the most part filled with ionized gas. Generally, this gas is hot hydrogen, whose density here is 10 times less than that in interstellar environment, namely less than 1 atom to 1 cubic decimeter. There are also heavier elements to be found here as well, like carbon, oxygen and silicon. Some part of intergalactic gas is concentrated in clouds differing from each other very much in terms of density and temperature. Interestingly, the chemical composition of their gas is diverse. It may contain atoms of hydrogen, helium, carbon, nitrogen, oxygen, sulfur and various metals. It is this gas that more likely than not feeds stellar formations in all galaxies. There are also much larger objects to be found in intergalactic space. For example, stars were spotted there quite recently. The total number of intergalactic stars in the observable universe may reach several trillion. Within the Milky Way alone, around 650 of these rogue stars have been pinpointed so far. As a rule, intergalactic matter doesn't emit any light and is mostly invisible to the potential observer. That is why its discovery was actually made by pure chance. It all started with quasars, which were discovered in the 1960s. Very soon, scientists noticed that the light from the quasars had certain missing pieces in some spectra. These particles were absorbed by something in between quasars and astronomers' telescopes. It later transpired that this invisible matter was the gas of the intergalactic medium, the IgM. In the decades that followed, vast accumulations and filaments of gas and heavier elements were discovered in intergalactic space. And even though at first glance it appears to be empty, its dimensions are so mind-blowing that there must be more matter evenly distributed around it than there is matter in all the galaxies of the observable universe combined. It is safe to assume that some part of intergalactic gas has been left out there after the hypothetical Big Bang. Still, as there are heavier elements in its composition, it may only mean that many of these elements used to be part of interstellar dust lost by other galaxies. Intergalactic gas actually plays an important role in the process of the universe's evolution. Under the influence of a galaxy's gravitational pull, gas is gradually sucked into galaxies at the rate of 1 solar mass a year, which is quite close to the rate of star formation in the disk of the Milky Way. Apart from that, matter exchange among all galaxies occurs thanks to this process. The point is that stars in a given area of the universe collapse and release part of their matter in intergalactic space. Having been released, the matter becomes part of intergalactic gas and so later takes part in the processes of star formation in other galaxies. Consequently, star formation in galaxies will not stop while there is still intergalactic gas around pulled by gravity. A substantial portion of intergalactic gas is matter remaining after supernovae, which is why temperatures in some areas of intergalactic environment are extremely high, sometimes reaching as much as several million degrees Celsius. The high temperature of some areas may also be accounted for by electromagnetic radiation emitted by intergalactic black holes following matter accretion on their surfaces, or else by powerful streams of energy emitted by still more massive black holes. Intergalactic gas plays the role of raw material in star formation, while intergalactic space is some sort of a tank used for its storage. The mechanism of intergalactic gas recirculation hasn't been studied deeply enough. First of all, because unlike galaxies, which are bright and easily seen, this gas emits no light to speak of. In their attempt to study this phenomenon, astronomers have devised supercomputer Foggy. Foggy modeled the patterns of intergalactic gas movements, and it is possible to observe how gas traveled around galaxies in the course of 13 billion years. Most of this matter is carried to intergalactic environment by stellar wind, that is thanks to the process of matter flow from stars to areas beyond their galaxies. It should be mentioned that this occurs when particles in a star's atmosphere accelerate to speeds exceeding the escape velocity of this star. Stellar wind is crucial for stellar evolution. As a result of this process, the mass of a star diminishes, and the intensity of this process has a direct impact on this particular star's lifespan. Also, stellar wind is capable of carrying matter enormous distances through space away from its departure point, as it were. Moreover, it may have an impact on matter around it by sharing some of its kinetic energy. Results of this process may be clearly observed in the shapes of some galaxies or nebulae. For instance, the emission nebula NGC 7635, nicknamed Bubble, assumed its shape as a result of this process. And in the case of galaxy M82, also known as the Cigar Galaxy, we can observe how stellar wind from a great number of stars caused clearly seen matter ejections from the galaxy. Apart from the debris left over from supernovae, there is also intergalactic dust to be found in this environment. Today, it is posited that it is intergalactic dust that is to blame for jinxing estimations of distances on the intergalactic scale. For example, when supernovae, quasars or other galaxies are being observed. Among its many properties, it is capable of forming clouds. By 1980, 4 such nebulae had been pinpointed within several megaparsecs from the Milky Way. As for intergalactic stars, they are rather difficult to detect and explore. Some of them have been spotted in the X-ray spectrum with the help of the Chandra X-ray Observatory. Many of them are binary systems made up of one regular star as one component and one compact heavy object like a black hole as the other. When such celestial bodies lie close to each other, the more massive component attracts matter from the regular star. While flowing to its new host, matter spirals away from its source to form an accretion disk. This disk compresses and heats up to extremely high temperatures, and as a result, it does not simply become luminescent, but starts emitting X-rays. It is next to impossible to spot most objects of this kind using regular telescopes. Meanwhile, rogue stars inhabiting voids may eventually prove to be quite a common thing, rather than something extraordinary. And perhaps about half of starlight is actually emitted by stars lying beyond the boundaries of galaxies. It is hard to tell how big their number may be. Distances from the Milky Way to other galaxies are by all accounts mind-boggling. As a rule, it is anything from millions to billions of light-years. Due to the universe's cosmological expansion, the distance between the Earth and any remote object in the universe is constantly growing. which makes the light emanating from this object look redder than it actually is. This phenomenon is known as a redshift. It is of great help in gauging distances and velocities on the astronomical scale. Alternatively, some galaxies' spectrum is blue-shifted, which means that they're not on an escape trajectory from us, but on the contrary are moving to meet us. One of these unusual space objects is the galaxy M86 in the Virgo cluster. Roughly 52 million light-years away from the Sun, it is moving towards the Milky Way at a speed of around 244 km per second, which makes it one of the fastest-moving blue-shifted galaxies. By moving at a high speed through the scattered gas the Virgo cluster is filled with, M86 is constantly shedding its own interstellar matter. As a result of this process, it leaves a trail of long lines of warm ionized hydrogen behind. M86 is connected with the almost destroyed spiral galaxy NGC 4438 with several of these filaments. These two galaxies are thought to have collided at some point in the distant past, which was the smaller one's undoing. Interestingly, M86 is known to have destroyed its other neighbors in the past as well. Several stellar streams have been detected in its halo that are likely to be the remains of smaller galaxies absorbed earlier. An impressive number of globular clusters in its structure is another outstanding feature of M86. Observations show that their number is upwards of 3,800, which is around 25 times as many as in the Milky Way. There is a theory that claims these clusters to be the remains of dwarf galaxies that M86 would have absorbed in the past. If it really is the case, then it would have destroyed tens or even hundreds of other galaxies. Having said that, M86 looks anything but unique. The galaxy ESO 137-001, which we'll be looking at next, has a similar shape. But unlike M86, it appears more outlandishly original. Located 227 million light-years away from the Sun, it is as heavy as 5 to 14 billion solar masses. As for its stars, most of them are young and bright blue giants. ESO 137-001 in its turn is part of Abell 3627, a large galaxy cluster. Moving to its center at an incredible speed of almost 2,000 km per second, the galaxy collides with interstellar gas pressure inside the cluster. As a result, its own gas is blown out, leaving behind tails that stretch for up to 260,000 light-years. Incidentally, the mass of interstellar gas in those areas is 2 to 4 times that of the gas inside the galaxy. It is hardly surprising that starbursts are a common thing here. That is, stars don't stop forming in these enormous streams made up mostly of hydrogen. When seen from the side, ESO 137-001 appears like a giant jellyfish floating through endless expanses of space. Unfortunately, as the galaxy is continuously stripped of its interstellar gas, its life expectancy diminishes too. With not much material left, no new stars can form here, which greatly affects the structure of the spiral arms and central bulge of the galaxy. On the bright side, scientists have a chance of finding out more about dark matter and its interaction with other space objects by observing the behavior of the gas streams left in the galaxy's wake. Speaking about the formation of new stars, there is a galaxy with a name that speaks for itself: Baby Boom. Around 4,000 stars are born here every year, which is about 400 times more than in the Milky Way. Straightforward calculations show that on average, a new star lights up in this area of space every 2 hours. The Baby Boom galaxy lies around 12.2 billion light-years away from the Earth. This means that what we see when observing it is what was happening just 1.5 billion years after the hypothetical Big Bang. It was a time when the universe was still in the process of forming its structure. What is taking place in the galaxy now is drastically different from what we expect to observe there in theory, based on what we know about star formation. The reasons why stars are produced here at such an astounding rate are not known yet, but it is beyond any doubt that Baby Boom is able to provide us with a lot of information about the early stages of our universe's evolution. One of the few galaxies one can observe through an amateur telescope is the so-called Sombrero Galaxy, official designation M104. It lies 30 million light-years away from the Sun, and its diameter is roughly 4 times smaller than that of the Milky Way. The Sombrero Galaxy's outstanding feature is a massive ring of dust and cold hydrogen enveloping it. Observations show that it is here that most young stars are born. In addition to the peculiar ring, the Sombrero Galaxy is also remarkable for its elaborate inner makeup. Observations with the Spitzer Space Telescope show that most stars in this galaxy form a structure typical of elliptical galaxies. The stars here are mostly rather old yellow and red dwarfs. The other stars here, on the other hand, form spiral structures concealed within an elliptical cloud. It is thought that this phenomenon is a result of two galaxies' collision, with their stars subsequently and almost inevitably mingling together. It is incredible that the galactic structures survived a merge of that scale with minimal damage, are none the worse for this tremendous collision, and can still be observed. Another peculiar feature in the Sombrero Galaxy is exceptionally powerful X-ray radiation emanating from the center. It is assumed that the accretion disk of a supermassive black hole may be its source. The mass of the hole is estimated to be over 1 billion solar masses, which makes this enormous object one of the most massive black holes known to science today. There are also several sources of tremendously high frequency or terahertz radiation detected within the galaxy, although today their nature is still a mystery. Our galactic parade today is concluded with yet another object boasting an elaborate inner structure, the eerie M64 Galaxy, rather aptly dubbed the Black Eye Galaxy. The nickname comes from a dark band of cosmic dust that partly conceals the galaxy's center from the observer on the Earth. Due to this line of cosmic dust, as well as the exceptionally bright active nucleus, it is impossible to estimate the Black Eye's number of stars even roughly. What we do know is that it is comparatively small and not so remote. Its radius measures 25,000 light-years, and it lies approximately 17 million light-years away from the Milky Way. The Black Eye Galaxy is made up of two well-defined parts. Interestingly, the inner disk with a bulge rotates in the direction opposite to that of the outer ring. The most likely explanation for such a bizarre makeup is that the galaxy formed after two smaller ones collided and merged in the distant past. Admittedly, it would take a combination of a number of mutually independent factors for such a fascinating and well-defined structure to form. For example, the progenitor galaxies would have moved at specific velocities and come together at a certain angle. The odds of a success would have been minuscule. In terms of the vastness of the cosmos, our planet is just a small rocky fragment traveling at incredible speed through boundless emptiness. For billions of years, it has been orbiting the Sun, maintaining a distance of about 150 million kilometers. However, the true size of our system is much larger. According to modern concepts, its outer boundary, which is considered the far edge of the hypothetical Oort cloud, is at a distance of about 100,000 astronomical units. Beyond this boundary begins the vast abyss of the interstellar vacuum, space so rarefied that there is on average only a single hydrogen atom per cubic centimeter. The distances between the nearest stars in our part of the galaxy are a matter of a few light-years, and a photon that has left the Sun can reach Proxima Centauri without ever colliding with a particle of matter. This vast void is a pervasive and integral part of the deep structure of the cosmos. It permeates the entire Milky Way, separating stars and planets, black holes and white dwarfs, super-dense pulsars and scattered nebulae. If you move outside the galaxy, you can see that it is surrounded by an even deeper vacuum. For example, between us and the Andromeda Galaxy lies 2.5 million light-years of exceptionally rarefied space. This distance is so great that 25 galaxies like ours could fit in it, yet it is filled only with the deepest cosmic vacuum. And this is only a small part of the great cosmic abyss. The Milky Way, the Andromeda Nebula and the Triangulum Galaxy, as well as about 100 of their satellites, are bound together by pervasive invisible threads of gravity. This structure is called the local group and is a large cluster of cosmic matter about 10 million light-years in diameter. The local group, in its turn, is part of an even larger formation, but a relatively small galactic filament by the standards of the universe, called the local sheet. This flattened structure, consisting of several hundred galaxies, has a diameter of about 46 million light-years, and its thickness is roughly 5 million light-years. The sheet is also part of an even larger association called the Virgo supercluster. However, very close to the local sheet, outer space suddenly changes its appearance. Here, the usual colorful universe is harassed by a giant black abyss known as the local void. In fact, the local sheet is one of its walls, the other conventional boundaries being the Perseus-Pisces supercluster and the Pavo-Indus supercluster. At the same time, the void is divided into conventional parts by several rarefied galactic filaments, and wide passages link it into a single network with the neighboring Sculptor and Hercules voids. Due to the cosmological expansion of the universe and the gravitational influence of the surrounding matter, the volume of the local void is slowly increasing. At present, its diameter is about 150 million light-years, and the distance to the center is at least 70 million light-years. Meanwhile, the nearest edge of this cosmic void is located very close to the Earth, at a distance of about 3.2 million light-years. Due to this proximity, the local void occupies a significant part of our planet's night sky, about 40%. The main plane of the Milky Way, containing many bright stars and large nebulae, covers the central part of this region from us. Still, its edges do remain accessible for observation. In 1854, a dwarf spiral galaxy was discovered a little north of the constellation Hercules. It was dubbed NGC 6503. Later, with the advancement of observation techniques, it became known that it is located in the middle of the local void, and its distinguishing feature is the incredible multicolor appearance. The spiral arms of the galaxy are permeated with bright red clots of heated hydrogen, and shining blue nebulae are stellar nurseries. The center is obscured by clouds of cool gas and dust, which have a noble brown color. NGC 6503 has a diameter of about 30,000 light-years, and its distance from Earth reaches 17 million light-years. Due to the gravitational pull of the Virgo supercluster, this galaxy is approaching us at a speed of about 43 kilometers per second. It is believed that its gradual approach to the local sheet will eventually saturate its space with interstellar hydrogen, causing an increase in star formation. It is estimated that in a few billion years' time, the current number of young stars could double, and the small galaxy will shine with renewed vigor. The motion of NGC 6503 is a clear demonstration of how the voids are likely to have come about. It is believed that the foundations of the large-scale structure of the universe were laid in the first minutes of its existence, at the time of chaotic mixing of matter and energy. Cosmic cataclysms of incredible power shook the young universe, forming local compactions and voids. Subsequently, clots of matter became proto-galactic clouds, and areas of space of reduced density became voids. Over time, the pervasive influence of gravity intensified this contrast, pulling stars and cosmic gas into relatively dense clusters, making the space and voids even more rarefied. Observations show that the vast majority of galaxies formed between 10 and 13 billion years ago. In addition, no significant differences have been found to exist between the age of galaxies located in voids and those that form global filaments. This fact also confirms the modern theory of the formation of the large-scale structure of the universe. Meanwhile, allowing for the cosmological expansion of space, we can assume that with time, the local void will become larger and more rarefied, and the Virgo supercluster will gradually disintegrate into several independent groups. At present, it is an association of about 30,000 galaxies concentrated in a region of space with a diameter of about 200 million light-years. At the same time, the total mass of the cluster is about 1.5 quadrillion solar masses, which is tantamount to about 1,000 galaxies such as the Milky Way. The Virgo supercluster is partially contiguous with two other galactic superclusters, the Centaurus and Pavo-Indus superclusters. At the same time, its other side borders on a vast region almost devoid of matter. It is called the Taurus void and is one of the largest known cosmic voids. It is rather difficult to study this part of outer space. The reason is that most of the void lies in the so-called zone of avoidance, a sector closed off from us by the Milky Way plane. The bright stars in our galaxy outshine the fainter and more distant sources, and interstellar matter absorbs and scatters their light. However, thanks to infrared studies, we do have some ideas about the structure of this void. The diameter of this tremendous void is about 200 million light-years, and the distance to the center is about 150 million light-years. When observing the void, one is immediately struck by the remarkably clear boundary between the relatively empty space and a bright cluster of galaxies located much further away. It is called the Perseus-Pisces supercluster and is one of the largest in this part of the universe. A transition this sharp is characteristic of dust clouds, even though infrared studies do not confirm their presence. In all probability, the clear boundary between the void and the supercluster is caused by gravitation, but the exact mechanism of their action still remains to be found out. Meanwhile, it is thought that the Taurus void, like most other cosmic voids, is not quite as empty as one might imagine. The way light passing through it is distorted suggests that this region may hide in its depths giant gas and dust clouds, the cradles of future galaxies. According to other hypotheses, huge masses of dark matter, the most mysterious substance in the universe, the properties of which are still not fully understood, may be contained inside the void. According to the most daring ideas, there are clots of antimatter or even more exotic matter with negative mass in the centers of cosmic voids. Nevertheless, despite their boldness, these hypotheses lie outside the boundaries of generally accepted scientific concepts, which makes it difficult to verify them experimentally. Currently, only 2 separate galaxies have been discovered tucked away in the space of the giant void. One of them, UGC 2627, has a spiral structure and resembles the Milky Way, while the second, known as UGC 2629, is an elliptical dwarf galaxy. Both objects are located almost in the heart of the void, at a distance of about 185 million light-years from us. The distance between them is small and is within a few 100,000 light-years. Perhaps there are other single galaxies hiding in the space there, but the Milky Way disk does not allow us to see them. Meanwhile, the Virgo supercluster, together with 4 other superclusters, forms a giant galactic filament called Laniakea. It contains more than 100,000 galaxies and stretches for more than 500 million light-years in space. Its gravitational center is the Great Attractor, a mysterious supercluster of galaxies located 250 million light-years from Earth. In its turn, Laniakea is part of a vast galactic stream, and further out, one can see that most of it is surrounded by a black abyss of unprecedented proportions. The light of distant galaxies is drowned in its emptiness. and even the mysterious and elusive neutrinos take billions of years to cross this cosmic abyss. To be honest, it is hard to believe that despite all the development of observational technology, such a gigantic void was noticed only 10 years ago. The year 2013. The University of Wisconsin-Madison. A team of astronomers led by Professor Amy Barger is working to determine the distance between galaxies. In the process, an unexpected and staggering fact is discovered. It turns out that Laniakea and most of its surrounding superclusters are enveloped by a cosmic void of unprecedented proportions. After making calculations, scientists discovered that its diameter exceeds that of any previously known void. The size of the discovered void turned out to be so enormous that several fundamental cosmological principles were questioned. It appears that the universe is much more elaborate than we imagined. The research done by Amy J. Barger, Ryan Keenan and Lennox Coey has led, in all likelihood, to one of the greatest astronomical discoveries of recent years. Their work has shown that our galaxy, along with its surroundings, is located in the middle of the largest supervoid known to science. It was named KBC, after the first letters of the discoverers' names. Observations show that the shape of the giant void is close to spherical, and its diameter may exceed 2 billion light-years. According to calculations, the Milky Way is located a few 100 million light-years from the conditional center of the Great Cosmic Abyss, and about the same distance from its edge. The discovery of a giant bubble of emptiness surrounding Laniakea helped to explain the paradox that had kept scientists busy for many years. The fact is that all galaxies in the universe are gradually floating apart due to cosmological expansion. Measuring the speed of this motion allows us to calculate the so-called Hubble constant, a fundamental physical constant characterizing the rate of expansion of space. However, if we take the galaxies closest to us to calculate the Hubble constant, it turns out that the rest of the universe is expanding too slowly. On the other hand, if we take distant objects as the basis, the Milky Way's surroundings are moving faster than they should. The discovery of the void has accounted for a lot. The fact is that the galaxies inside it, including the Milky Way and its neighbors, are constantly experiencing additional gravitational influence from objects outside the void. This creates an additional force that gradually stretches our cluster in different directions. It is also surprising that the KBC void is so huge that it comprises not only superclusters of galaxies, but also other voids. For example, the local void, as well as the torus void, are part of its structure. It turns out that compared to other voids, even though KBC looks large, it isn't quite so empty. Nevertheless, according to calculations, even this void is just a barely noticeable dark spot against the background of the observable part of the universe, the diameter of the latter reaching 92 billion light-years. If we look at the global map of the universe, we will see a lot of dark spots on it, close to the KBC void in terms of their size. Most of them easily fit within the framework of modern physical theories, while others show surprising and strange properties, difficult to explain from the point of view of science. And one of the most noticeable riddles of this kind in space is the Eridanus supervoid, also known as the CMB cold spot. It is estimated to have a diameter of 500 million to 1 billion light-years, and it lies at a distance of between 6 and 10 billion light-years from the Milky Way. This means that this formation is one of the most extensive elements of the large-scale structure of the universe. The void is located in the southern hemisphere of the Earth's sky and occupies an impressive area on it. several times larger than the full moon. However, it is impossible to see it with the naked eye. The CMB cold spot is visible only with the help of special telescopes that study the cosmos in the microwave spectrum. Thanks to these, astronomers have discovered that within the spot, relic CMB radiation of the universe is about 70 microkelvin colder than the metagalactic average. This deviation is nearly 4 times as intensive as the strongest anomaly previously recorded, and its gigantic size makes it a truly enigmatic object that requires extensive study. It is now believed that relic CMB radiation traveling through hundreds of millions of light-years of deep vacuum is gravitationally influenced by distant galactic superclusters. This causes the pervasive echo of the Big Bang to lose energy, making the CMB cold spot appear cooler in images than its surroundings. Nevertheless, this effect cannot fully explain the excessive cooling of relic radiation. According to calculations, the attraction of external galaxies can account for only a quarter of the observed deviation. It is assumed that the remaining 75% of the effect may be due to the impact of hypothetical dark matter or dark energy concentrated in the depths of the void. However, it is going to take a while before we can truly unravel this cosmic mystery. The history of the largest modern orbital telescope began back in 1996. Its development and modernization took as long as 25 years, after which the spacecraft left our planet and set out on its journey through space. It took James Webb a month to reach its destination point, located 1.5 million kilometers from our planet. Because the telescope is equipped with high-precision infrared sensors, it can see the dimmest and most distant space objects hidden in the depths of the universe. However, this unmatched sensitivity also has a downside. The intense radiation from the Earth, the Moon and the Sun interferes with the faint signals of distant stars and exoplanets. Therefore, in order to counteract this effect, the supersensitive instruments were covered with a multi-layer heat-reflecting screen. The observatory itself had to be moved away from large celestial bodies and be located near the so-called second Lagrange point in the shadow of our planet. Still, the obtained results were absolutely worth all the effort, because James Webb helped us make quite a number of amazing discoveries pretty much from the very first days of its operation. With some of them quite expected, others, on the other hand, prompted additional questions. One of the studies with a paradoxical outcome was the spectral analysis of WASP-96b, a glowing exoplanet of extremely low density. It is located 0.045 astronomical units from its parent star and completes a full orbit around it in just 3.5 days. According to calculations, the mass of the celestial body is half the mass of Jupiter, and its diameter is 20% more than that of Jupiter. Because of the extreme proximity to the star, the temperature of the object's outer layers is quite high and reaches 1285 Kelvin, or just over 1000 degrees Celsius. Exoplanets of this type fall in the category of hot Jupiters and are distinguished by large losses of atmosphere due to stellar wind. Earlier measurements showed very clear lines of sodium in the atmosphere of WASP-96b, which was interpreted by the researchers as a sign of an unusually clean and cloudless atmosphere. The fact is that according to the available models of the structure of gas giants, this element can exist only in the planet's interior. As we can see traces of it, it means that the upper regions of the celestial body's atmosphere practically do not absorb light. It was assumed that thanks to this, the ultra-sensitive detectors of James Webb could look into the deepest layers of the exoplanet. However, the information obtained by the telescope turned out to be radically different. The outer layers of the gas giant contain great amounts of water vapor. It condenses in the upper atmosphere and can form a large haze or thick clouds, reflecting some of the light shed on it. Because of this, the temperature of the lower layers of the object may differ significantly from the calculated values. Perhaps the accuracy of the earlier study was insufficient, or else some of the data was misinterpreted. It is also possible that we do not yet know of a certain factor that would allow us to combine the results to form a single correct picture. WASP-96b remains a mystery, which means it still needs to be studied in more detail. Of course, James Webb's discoveries do not end there. For example, 69 light-years away, there is an unusual system consisting of 3 brown dwarfs at once. These cosmic bodies are too big to be planets and at the same time too small to launch a stable thermonuclear reaction in their interior. Brown dwarfs are usually difficult to detect, as the radiation of their surface is extremely low. But James Webb sees the universe primarily in infrared, which makes it easy to distinguish objects that are virtually invisible in the optical range. The 2 largest components of the system are very similar in their characteristics and are located quite close to each other. The distance between them is about 2 astronomical units, and their total mass is slightly more than 100 times that of Jupiter. The temperature of both objects is relatively high, reaching 2600 Kelvin or slightly over 2300 degrees Celsius. The third component of the system is at a much greater distance, about 100 astronomical units from the center. Its mass is between 14 and 23 Jupiter masses, and its radius is 20% more than that of Jupiter. Also, this brown dwarf is about twice as cold as its more massive companions. Observations revealed that the temperature of its outer layers is 1240 Kelvin or slightly below 1000 degrees Celsius. Nevertheless, the celestial body is considerably warmer than the gas giants in our system, especially given the absence of a star that would give it heat. It was surprising to find that the outer layers of this brown dwarf contain not only the usual components such as water, methane or carbon dioxide, but also minute particles of various silicon compounds. The simplest of these is quartz, but more complex substances have also been detected. These are thought to be concentrated in the atmosphere of the celestial body in the form of vast clouds. The existence of such clusters had previously been predicted from theoretical considerations, because silicon, being a product of stellar thermonuclear reactions, is quite widespread in the universe. Still, until recently, observations have not been able to confirm this hypothesis. It is thought that about 140 million years ago, there was a single gas-dust cloud in the system's place, which later split into 3 independent clumps. This event may have been caused by the gravitational influence of a massive celestial body that passed close to the protostellar nebula. Remarkably, if the separation had not occurred, the total mass of the formed object would have been enough to start a self-sustaining thermonuclear reaction. In this case, instead of 3 brown dwarfs, we might have been observing a single tiny star. Incidentally, the James Webb equipment is capable of observing not only single objects tucked away in the depths of space, but tremendous space structures as well, that stretch for hundreds of light-years. One of them is the Carina Nebula, which is one of the largest stellar nurseries in our galaxy. This bright and vast cluster is located about 8,500 light-years from the Earth and has a mass of up to 900,000 suns. It contains not only giant clouds of interstellar gas and dust, but also thousands of stars, from the smallest ones to the most gigantic. This is where 2 of the Milky Way's brightest objects are located, Eta Carinae and WR25. The luminosity of each is several million times greater than that of the Sun. Unique objects like that certainly attract astronomers' attention. Besides, James Webb's infrared cameras are able to pick out great numbers of stars in the dusty haze, which were previously unknown to us. The point is that it is in this area in space that hundreds of young stars are constantly getting born. According to modern concepts, new stars are formed by gravitational forces that compress and heat up clouds of cosmic dust. During its evolutionary process, a protostar goes through several stages until finally a thermonuclear reaction kicks in its interior. This theory has been confirmed by multiple observations, but many details of this long and complex process currently remain understudied. The formation of a new star sometimes takes millions of years, but astronomers don't need that long to observe it. Thanks to James Webb's infrared sensors, thousands of protostars and young stars at various stages of evolution have been detected in the Carina Nebula. It is important to note that all these objects formed within the same gas cloud, which means that they're very similar in terms of composition and age. By observing them, researchers can fully trace the process of star formation and better understand what forces are involved. Some phases of this process, predicted only in theory, take hours or days, and with James Webb, the chance of capturing them is greatly enhanced. For all we know, we may soon be able to admire a photo of a young star flaring up thousands of light years from the Sun. Meanwhile, an 18-section mirror 6.5 meters in diameter and an onboard array of high-accuracy instruments allow James Webb to capture light from objects much further away, at the very edge of the visible universe. They are more than 13 billion years old, giving us a glimpse of the earliest times immediately after the hypothetical Big Bang. However, even James Webb would not have been able to see their luminescence but for one unique coincidence. The phenomenon of gravitational lensing has long been known to scientists. This physical phenomenon helps us to better see into the depths of the universe. And this is how it works. A powerful gravity generated by a massive body focuses and amplifies the light from a source behind it. Such an effect can be produced only on condition that a great many factors happily combine, so it is not surprising that it is one of the rarest phenomena in the universe. It is all the more surprising that while observing the galaxy cluster SMACS 0723, located about 4 billion light-years from the Earth, James Webb captured light of a space object passing through gravitational lenses as many as 3 times. In total, the radiation was amplified about 20 times, without which astronomers would hardly have been able to distinguish it from background noise. The object is thought to be a distant and very old galaxy, whose age is estimated to be 13 billion years. About 10 other star clusters have also been detected, which are thought to have originated between 200 and 700 million years after the genesis of the universe. According to some observations, they have a complex structure which takes tens of millions of years to form. This discovery will allow scientists to develop the existing ideas about the early stages of the universe's evolution and may even prompt to question its age. Unfortunately, we still know very little about such remote times, and James Webb will surely help us learn more about them. The Solar System is just one of the countless multitude of planetary systems scattered across our galaxy. As we know, it consists of a single star in its main sequence stage and 8 planets with their satellites. In addition, our system contains over 1 million small celestial bodies like asteroids, comets and meteoroids. The planet in the Solar System lying furthest, at least that we know of, is Neptune. Its orbit's radius measures around 30 astronomical units, which is equivalent to approximately 4 light-hours. Amazingly, only a tiny portion of the Solar System is encompassed by Neptune's orbit. The remotest object in the system discovered to date is the so-called Far Out, lying 132 astronomical units, or 18 light-hours away from the Sun. Still, even this object, barely visible against a dark background of unfathomable space, is not at all close to the hypothetical Oort cloud, whose inner boundaries lie approximately 2,000 astronomical units away from the center of our system. According to some estimates, its outer boundaries stretch for up to 60,000 astronomical units at the very least, which is around 1 light-year. These limits are predefined by the Sun's gravitational influence, and what lies beyond is interstellar space. Moving further away, we will notice over 50 of all kinds of stars within 20 light-years from the Sun. These stars are really diverse, from dim and cold brown dwarfs to bright and widely known objects like Sirius, Procyon and Altair. Some of them have their own planetary systems, with objects potentially capable of nursing and sustaining life. For example, the object known as Gliese 832c, which is 16.1 light-years away from the Sun, is similar to our Earth more than any other planet within the solar system that we know of. The average temperature on the exoplanet's surface reaches 253 Kelvin or 20 degrees Celsius below zero, and it takes the astronomical body just 36 Earth days to complete a full orbit around its parent star. In astronomical standards, the distance between us and Gliese 832c is relatively small. However, a space probe setting out from our system at a speed of roughly 17 km per second would take as much as 300,000 years to reach the exoplanet's environs. At our current level of technological advancement, it is impossible to design an interstellar spaceship capable of completing as long a journey as that. The solar system, together with its neighbor stars, is part of the Orion Arm. The latter, in its turn, is part of the Milky Way. It contains around 400 billion stars, and potentially over 1 trillion exoplanets of all sorts can be discovered there, according to estimates today. The main diameter of the Milky Way measures around 100,000 light-years, and the stellar halo may be twice as large. Even though the thickness of the main disk measures about 1,000 light-years, there is a clearly defined bulge in the galaxy's center. This bulge is roughly 3,000 light-years thick. The Milky Way is part of the so-called local group. This is a vast structure comprising over 50 galaxies concentrated within an area of space measuring around 10 million light-years in diameter. The Andromeda Galaxy, the Triangulum Galaxy and the Milky Way are the largest of the lot. Some estimates show that the mass total of the cluster may reach as much as 3 trillion solar masses, with our galaxy and Andromeda accounting for the major part. With the distance from the Earth to Andromeda around 2.5 million light-years, it is considered to be our closest galaxy, not counting smaller or dwarf ones. Moving on to the next order, the local group forms part of the giant Virgo supercluster made up of over 30,000 galaxies. The supercluster is located within an area of space with a diameter of around 150 million light-years. Its mass total is as much as 1 quadrillion solar masses, or in other words, around 1,000 galaxies like the Milky Way. The supercluster is quite flattened, and around 60% of all the objects it is made up of appear like a flat sheet around 10 million light-years thick. Staggering though it may appear on the face of it, this value is actually small in terms of the large-scale structure of the universe. As we zoom out still more, we have a chance of seeing a giant supercluster of galaxies approximately 520 million light-years in size. Called Laniakea, it includes several galaxy superclusters, among others the Virgo supercluster and the Great Attractor. The overall mass of this formation measures approximately as much as 100 quadrillion solar masses. The Great Attractor lies roughly 250 million light-years away from our planet and is the gravitational center for all objects lying close by astronomical standards. It cannot be observed from the Earth directly, as the Milky Way's plane thwarts it. That is why the nature of the Great Attractor still remains an unsolved mystery today. Laniakea is part of the large-scale structure of the universe, an elaborate system of galactic filaments, wars and voids, gargantuan areas of emptiness in space. Some of these objects are really incredibly enormous. For example, the Hercules Corona Borealis Great Wall stretches for around a staggering 10 billion light-years. Ever since its discovery in 2013, this superstructure has been considered the most gigantic component of the large-scale structure of the universe. To all appearances, it must be home to millions of galaxies, and the number of stars it contains will probably always defy calculation. The mere existence of a structure like that is a mystery to science, as according to today's accepted theory of universe's evolution, gargantuan clusters like that are simply not supposed to form. But incidentally, this wall, so enormous that the human brain cannot fully appreciate its dimensions, is still just a tiny portion of the observable universe. According to today's cosmological notions, space and the universe is continually expanding, with the speed of expansion depending on the distance between objects. The further an observed object lies away from the observer, the faster the distance between the two increases. The rate at which the two mutually recede is not limited by the speed of light, because it's actually space matter that is expanding, which means that at a certain point the two objects will be mutually unobservable. Relic radiation observation shows that the area of the observable universe is a sphere, with a diameter roughly 93 billion light-years. According to the theory of relativity, we can see and interact with only those objects that are within this sphere. This conventional spherical area in space is called the meta-galaxy, and it may be either all of the universe, or again its tiny portion. For all we know, hypothetically, there may well lie some unknown structures beyond the visible boundaries of space. Such entities are referred to as extra-metagalactic objects, and unfortunately it is impossible to study them today with scientific methods. Still, some astronomical bodies on the edge of the visible universe appear to be moving in ways different from what we would naturally expect, judging by the data we have. Instances of anomalous movements like those may be evidence of the presence of some massive structures beyond the metagalaxy boundaries. Their attraction pervades the space around and influences objects around too. There is a whole plethora of hypotheses as to the structure of the universe beyond the metagalaxy, but most of them are rather of metaphysical nature. For example, some people believe that time and space, as we more or less know them, are non-existent beyond the boundaries of the universe. The physical laws we're used to do not apply there either, and notions of matter, material, or energy are virtually senseless. This hypothesis is further elaborated on by the following idea. The metagalaxy accounts for just a part of a yet more complex and larger-scale superstructure in space whose makeup and dimensions are too incredible for us to imagine. It is quite possible that this structure could be in a multidimensional space, or else be based on physical principles we have no idea of. This makes the metagalaxy just an insignificant addition to or a partial reflection of this mind-boggling superstructure. According to some interpretations of the anthropic principle, there are other worlds out there beyond the boundaries of the observable universe. In those worlds, the values of the fundamental constants like the speed of light or the electron charge are completely different. This hypothesis is in many ways supported by the idea of a multiverse, which schematically appears as foam with lots of bubbles separated from each other by thin walls, but these walls are impenetrable. This makes every universe a separate space, with its own physical laws, and for all we know, these laws may be totally different from the ones we're used to. The most radical hypotheses go as far as to deny our world any objective reality whatsoever. According to these, the universe is just a simulation like virtual reality in computers, but on an incredibly advanced level. As a rule, ideas like that imply that there are some super beings or super civilizations out there beyond the reality we're used to, whose level of advancement is infinitely higher than ours and whose goals and capabilities are arcane and incomprehensible. However, it goes without saying that it is hardly possible to either confirm or repudiate these hypotheses. Space is a boundless ocean that stretches in all directions, with no beginning and no end. We can observe just a tiny part of this abyss, where only eternity and darkness reign. Lost planets and extinguished stars, giant nebulae and whole galaxies sink without a trace in its blackness. Even the indomitable light gradually disperses and melts in these infinite expanses, and with each passing moment, the universe expands ever more, thus becoming even more mysterious and beating our understanding of it.